Okay, now let us start with the idea of tensor functions. Now, tensor functions are quantities that can be functions of tensors. For example, phi of x is a scalar valued function of a scalar or a zeroth order tensor. So these kinds of functions you are very familiar with. This outputs a scalar and the input to it is also a scalar. Okay, these are the functions that we are familiar with. You can have functions like which are scalar valued, let's say temperature over a space. So phi is the temperature over some Cartesian space xyz, which is given as a function of x1, x2, and x3, which we can also write as phi of let's say x. So the position vector x. So that means that this is now a scalar valued function of a vector, which is the position vector in this case. So this is a scalar valued function of a vector. Similarly, we can imagine that we have scalar valued functions which depend on some second order tensor A. So this outputs a scalar, but the input to it is a second order tensor. Okay, so we can generalize this actually further. We can think of a vector valued function which is a function of the position vector at a point. Say this might be the velocity of a particle in a fluid, where velocity itself is a vector, but it varies from point to point. So this is a vector valued function of a vector. Okay, generalizing this is not difficult. We can have a tensor valued function t, which is a tensor. Let's say stress. We have promised that we'll prove that stress is a tensor. So we have a stress that is a function of some other scalar, some other second order tensor, let's say strain. So this is a, a tensor valued function of a second order tensor. Okay, so these are the very many kind of possibilities that we have when we deal with when we expand the idea of a variable from a scalar to a tensor. So we can have various kinds of combinations. We can even have higher order tensor valued functions, which are functions of higher order tensors as well. Now the question that arises now is, how do we look at the variations of this? That means, how do we take derivatives of this? How do we answer the question at how does phi in this case, for this case, how do we answer the question and how does phi vary if I change A? So what would be, for example, the derivatives of phi with respect to A? If you ask me derivatives, in this case, if you ask me derivatives of phi with respect to x, I know how to do it. What I do is, I will do simply this. I will take the phi and change the x by a small amount, h. Uh, then I have the value at the old position, x, divide by h, make h tends to 0, and that would give me the variation of phi with respect to x. So if I perturb x a little bit and divide by the amount of perturbation, that would give me the rate of change of phi with respect to x. That is the idea that we have used so far, and that is the idea that you are familiar with. However, that idea has to be sort of generalized when we deal with an animal like this, which is a tensor which depends on another tensor. So we have to answer the question that how does this t vary? What is the variation of this second order tensor t when I change the input tensor A by a little bit? So that is what we are going to do in this part of the course. So let me go back to my notes. Okay, so this is what I talked about, that there can be various kinds of functions that we can now think of. So we can have vector valued functions, scalar valued functions, and tensor valued functions, which in themselves are also functions of a scalar, a vector, or tensor, or a mixture of them. So there are many possibilities. The easiest of these, easiest way in which well, the easiest kind of variation that we can think of is that we have a vector or a tensor which depends on time only. It doesn't depend on space, it just depends on time. So this is how we will write uh, vectors that are functions of time. So u is a vector which depends only on time. So it can be written as ui ei, where the components ui are functions of time. So these components are functions of time, and so we write it like this. So the derivative of u will be, I'm sorry, there shouldn't be a j here, it should be just ui dot t. I'll correct it. So ui dot t ei would be the derivative, the time derivative of u. So this is how we take time derivatives of vectors which are just functions of time. Similarly, if a second order tensor is a function of time, its time derivative would be tij dot ei ej. Remember, ei ej are fixed vectors, so neither them nor their dyadic products would change with time. So they are invariant with time, they are fixed vectors. So these components are functions of time. So you just take time derivatives of these components, and you are done. Okay. So let us do a small problem where we have this. We have a vector which is u cross v. Okay, so let's take this and let's work this out. Okay, so we have omega, which is given by u cross v. So uh, where u is a function of time and v is also a function of time, so we have to find omega dot is what. So obviously u can be written as ui ei, v can be written as v j ej, and we know that omega can be written as e I j k u j v k e I. This is how we write the cross product of. So when we do, therefore, omega is only a function of time. This is a fixed third order tensor, and this won't get affected by this dot. So we will have e I j k, and then we do u j dot v k plus u j vk dot, and then ei won't be affected by the time derivative. So this would be the components of omega dot. So this is how you handle vectors which are, you handle derivatives where the quantities involved are simply functions of time, not functions of space. Okay, let's stop here.